Utilizing advanced telescopes to study the fluctuations in light as the planet transits its star, astronomers have detected the presence of various elements, including water vapor and possibly even heavy metals. These insights not only help us understand this alien world, but also contribute to our broader knowledge about the diversity of planetary atmospheres in the universe. Each finding about WASP 121b paints a vivid picture of extremes, inviting us to ponder the mysteries hidden among the stars. The discovery of the exoplanet LHS 1140b has significantly shifted our understanding of potentially habitable worlds. This intriguing planet lies about 43 light-years away in the constellation of the Sculptor. Its size and mass position it nicely within the category of super-Earths, which are rocky planets larger than Earth but smaller than Neptune. What makes LHS 1140b particularly fascinating is its location within the habitable zone of its star, where conditions might be right for liquid water to exist, a crucial factor for life as we know it. What sets LHS 1140b apart from other similar planets is its substantial atmosphere, which scientists believe could harbor the elements necessary for biological processes. Its density suggests it likely has a solid surface, and studies show that it may possess a thick layer of clouds that could regulate temperature variations. This combination of size and atmosphere challenges the traditional notion that only Earth-like planets are suitable for hosting life. In other words, the criteria for habitability are becoming more flexible, suggesting that the universe might be teeming with diverse environments where life could arise. Moreover, the star that LHS 1140b orbits is a red dwarf, which is more stable than many other types of stars. Although these stars can emit radiation that might be harsh on nearby planets, the prolonged cold phase of red dwarfs gives planets like LHS 1140b a longer window for conditions to stabilize and potentially support life. This discovery urges scientists to rethink how they define habitability, recognizing that planets outside our solar system can bring new complexities to the search for extraterrestrial life. Ultimately, LHS 1140b serves as a reminder of the vast possibilities within our galaxy. It encourages researchers to widen their search criteria and consider a more extensive array of planetary environments that might support life. As we continue to study LHS 1140b and similar exoplanets, we are just beginning to scratch the surface of discovering what makes a world potentially habitable, broadening our perspectives and igniting our curiosity about life beyond Earth. International collaborations have become a cornerstone in the study of exoplanets, offering unique advantages that no single country could achieve alone. These partnerships bring together some of the brightest minds in astronomy from around the globe, enabling the sharing of ideas, resources, and technology. By pooling expertise and funding, researchers can take on larger projects that push the boundaries of what we know about planets beyond our solar system. One significant benefit of international teamwork is access to a diverse array of telescopes and observational tools. For instance, while one country may house a powerful ground-based telescope, another may operate a space telescope equipped for different wavelengths. Using these various facilities in unison can enhance data collection, allowing scientists to observe exoplanets from multiple perspectives. This comprehensive approach not only enriches the data, but also helps validate findings, leading to a more reliable understanding of planetary characteristics. Additionally, these collaborative efforts often involve different scientific disciplines, such as chemistry, geology, and atmospheric science. Interdisciplinary teams can analyze exoplanet atmospheres, interpret spectral data, or simulate planetary formation processes, creating a more robust framework for understanding these distant worlds. This integrative approach helps refine our theories regarding how exoplanets form and evolve, as well as their potential habitability. Finally, international collaborations also play a crucial role in fostering a global scientific community. They promote knowledge exchange, encourage innovation, and inspire the next generation of astronomers. Engaging young researchers in collaborative projects cultivates a shared enthusiasm for exoplanet research and leads to new discoveries that excite and expand our understanding of the universe. Ultimately, through cooperation, countries can accelerate the pace of discovery and deepen our understanding of exoplanets, those intriguing worlds that remind us of the vastness of the cosmos. The search for exoplanets, or planets outside our solar system, has become a vibrant area of scientific exploration, with several exciting global projects currently underway. One of the most prominent initiatives is NASA's Transiting Exoplanets Survey satellite, commonly known as TESS. Launched in 2018, TESS is designed to survey nearby stars for transiting planets, observing their dips in brightness as planets pass in front of them. By focusing on bright stars, TESS aims to identify candidate planets that follow-up missions can study in greater detail. Another key player in exoplanet research is the European Space Agency's Plato mission. Set to launch in the coming years, Plato will build on the techniques developed by TESS, aiming to find Earth-like planets orbiting stars similar to our own Sun. With its unprecedented capability to monitor thousands of stars simultaneously, Plato will assist in analyzing light curves that reveal critical information about planetary size, orbit, and potential habitability. Here on Earth, ground-based telescopes are also making significant advancements in exoplanet detection. Projects like the Very Large Telescope in Chile utilize high-precision techniques to directly image exoplanets and gather information about their atmospheres and compositions. Additionally, the Keck Observatory in Hawaii leverages the power of adaptive optics to minimize distortion from the atmosphere, allowing astronomers to measure the light from planets and gain insights into their characteristics. As technology evolves, the future looks promising for exoplanet exploration. Missions like the James Webb Space Telescope, which launched in late 2021, will delve deeper into the atmospheres of these distant worlds, analyzing chemical signatures that might suggest the presence of water, organic molecules, or even signs of life. The collaborative efforts of these global projects highlight humanity's relentless curiosity about the cosmos, ushering in a new era of discovery in our quest to understand the universe and our place within it. The quest to understand exoplanets, or planets orbiting stars beyond our solar system, is a complex and multifaceted endeavor. It draws from diverse scientific disciplines, each adding its unique perspective and expertise. Astronomy plays a leading role by identifying and cataloging exoplanets, using telescopes to detect their light and measure their distances from Earth. Techniques like transit photometry and radial velocity have revolutionized our ability to discover these distant worlds, revealing that many are likely to have conditions suitable for life. However, it's not just astronomers who contribute to this field. Planetary science helps us understand the formation and evolution of these distant planets. By studying our own solar system, scientists can infer processes that may occur around other stars. This comparative approach allows for the enhancement of theoretical models about planetary atmospheres and surface conditions. Insights from planetary geology assist in predicting what materials might exist on exoplanets, which is critical when evaluating their potential habitability. Climate science adds another layer of understanding. By examining how atmospheres behave under various conditions, scientists can simulate what weather and climate might be like on exoplanets with different atmospheric compositions. This is particularly vital for exoplanets within the habitable zone, where temperatures could allow for liquid water to exist. Researchers in this field can share knowledge about greenhouse gases and their effects, shaping our expectations of diverse climates across the universe. Finally, astrobiology ties everything together by asking the fundamental question: could life exist on these planets? By examining extreme environments on Earth, astrobiologists explore the limits of life, strengthening our hypotheses about where life might thrive beyond our planet. The collaboration between these disciplines creates a rich tapestry of knowledge, revealing not only how exoplanets form and evolve, but also how we might one day encounter life far beyond our own solar system. Exoplanets, or planets outside our solar system, have revolutionized our understanding of both planetary formation and the principles governing them. For decades, scientists formulated theories based largely on our own solar system, expecting to find planets that resembled Earth or the gas giants of our system. However, the discovery of exoplanets has revealed a stunning diversity in size, composition, and orbital patterns, raising questions about the mechanisms of planet formation and the processes that govern them. One of the significant surprises has been the existence of gas giants orbiting incredibly close to their stars, a category known as hot Jupiters. Their presence challenges classical planetary formation models. which suggested that gas giants would only form in the cooler outer regions of a solar system. These unexpected findings push scientists to reconsider and refine their theories to account for how such massive planets could form in such extreme conditions. This shift not only enhances our understanding of planetary dynamics, but also reflects on the processes that might be at play in different star systems across the universe. Then, we have the quantum aspects of the materials that make up these worlds. Exoplanet observations have led to the exploration of how quantum mechanics, the branch of physics that describes the behavior of matter and energy at very small scales, affects planetary atmospheres and climates. For instance, the interaction of light with molecules in different planetary atmospheres creates unique spectra. Analyzing these spectra allows scientists to determine the composition of exoplanetary atmospheres, which in turn may offer insights into the fundamental quantum behaviors of materials under various temperature and pressure conditions. Exoplanets are not just curiosities in our night sky, they are vital pieces of a much larger puzzle. They compel scientists to challenge and refine existing theories, revealing that our understanding of quantum mechanics and planetary formation is still growing and evolving. As we continue to discover new exoplanets and deepen our understanding of their environments, we may uncover even more revolutionary insights that reshape our knowledge of the cosmos. The discovery of life on an exoplanet would fundamentally reshape our understanding of consciousness and intelligence. Currently, we tend to view consciousness and the capacity for intelligent thought as phenomena deeply tied to the unique evolutionary paths taken by life on Earth. If life were discovered beyond our planet, it would invite us to reconsider what factors contribute to consciousness. Is it a rare fluke of evolution, or is it a common outcome in the universe, potentially arising under a variety of conditions? Additionally, this discovery could challenge the notion that consciousness is exclusively linked to complex organisms. Imagine a planet populated by simple microbial life, yet those organisms display forms of awareness or responsiveness that hint at primitive forms of consciousness. This raises intriguing questions. What does it mean to be alive or aware? If simpler life forms can exhibit a rudimentary form of intelligence, our understanding of consciousness might need to expand to include a spectrum of awareness rather than a binary distinction between sentient and non-sentient beings. Furthermore, finding intelligent life forms could stimulate profound philosophical inquiries. If an alien civilization has developed its own metrics of intelligence and consciousness, we might see alternative models that differ fundamentally from human experiences. This could lead us to understand consciousness not as a definitive goal of evolution, but rather as a diverse toolkit with varied uses tailored to specific environmental challenges. Ultimately, the implications for theories of consciousness and intelligence extend far beyond scientific curiosity. They may inspire new ways of thinking about our place in the cosmos and prompt a reflection on our definitions of life itself. Exploring the diversity of consciousness across the universe could lead to insights that deepen our appreciation for the unique but interconnected relationship we have with all forms of life. The laws of physics, as we know them, are universal and apply on a grand scale throughout the cosmos, including on exoplanets, which are planets that orbit stars outside our solar system. These laws dictate everything from gravity to electromagnetism, shaping how these distant worlds form, evolve, and behave in their unique environments. For instance, the gravitational pull of a star governs the orbits of its planets, while the interactions of radiation influence atmospheric conditions, temperature, and potential habitability. When scientists discover exoplanets, they study their characteristics by applying the same physical laws observed within our own solar system. The boiling point of water, the force of gravity, and the principles of thermodynamics all come into play. For example, if an exoplanet is too close to its star, it could experience extreme heat, preventing water from remaining in liquid form. Conversely, a planet farther away might be too cold, leading to conditions that are inhospitable to life as we know it. However, the conditions on exoplanets can vary widely, leading to a fascinating array of environments. Some exoplanets orbit in what is termed the habitable zone, where temperatures allow for liquid water, a critical ingredient for life. Others might possess thick atmospheres that create greenhouse effects, trapping heat and potentially supporting a diverse range of chemical reactions. The laws of physics ensure that, regardless of these differences, we can predict certain behaviors based on their environmental conditions. Understanding these principles can help unravel the mysteries of these alien worlds. As astronomers gather data from telescopes and space missions, they employ the laws of physics to interpret the findings, whether it's identifying the atmospheres of strange gas giants or the rocky surfaces of seemingly Earth-like planets. Each discovery is a step towards grasping the complexity and variety of the universe, reminding us of the wonders that lie beyond our own planet. The discovery of exoplanets in multi-planet systems presents intriguing implications for our understanding of the universe. In systems where several planets orbit the same star, researchers can study the interactions and gravitational dynamics between these planets. This helps to shed light on how planets form and evolve over time, offering clues about the processes that may have shaped our own solar system. When we find planets that exist in groups, it suggests a different history of formation than those in solitary orbit. For instance, planets can influence each other's orbits, which may lead to more stable or unstable arrangements over vast periods. This interplay can inform scientists about the likelihood of different types of planetary systems evolving, as well as the potential for habitable zones where conditions might support life. Each new discovery adds pieces to the puzzle of planetary formation and migration theories. Conversely, single-planet systems shift our focus. They provoke questions about why that particular star has no companions, or whether it might form planets later. These solitary planets could also represent unique developmental paths that diversify the types of worlds in our galaxy. Discovering a growing number of single-planet systems invites dialogue about the many environmental factors that contribute to planetary existence. These findings enrich our grasp of planetary ecosystems. Understanding both types of systems provides essential insights into the complexities of formation processes, potentially improving our models of how life-sustaining planets emerge. As more and more systems are studied, we get closer to unraveling the mysteries of our universe and assessing the cosmic neighborhood where life might thrive. The gravitational influence of multiple planets can significantly shape the evolutionary trajectory of their star system. When planets orbit a star, their gravitational pulls interact in complex ways, influencing not only their own orbits but also the orbits of their neighbors. This interconnected gravitational dance can lead to changes in orbital shapes, distances, and even stability over millions of years. For instance, when a large planet like Jupiter moves around its star, its substantial mass can affect the orbits of smaller planets nearby. It can stabilize some orbits and destabilize others, possibly leading to collisions or ejections of smaller bodies. This interactive gravitational field not only dictates the fate of planets, but also influences the distribution and trajectory of smaller celestial objects, such as asteroids and comets. Moreover, these gravitational interactions can affect the star itself. They can influence the rotation of the star and its magnetic activity, which in turn can have profound effects on the habitable zones of the system. Changes in the star's magnetic field and solar output can greatly affect potential life-supporting conditions on planets within the system. The gravitational interplay among multiple planets plays a crucial role in both the stability and evolution of the star system as a whole. These dynamics can lead to the emergence of habitable environments or, conversely, conditions that may inhibit the development of life, ultimately shaping the story of that planetary system through the ages. Exoplanets, or planets beyond our solar system, exhibit an extraordinary variety of orbits and alignments, which reveal much about their formation and the dynamics of their systems. One of the most compelling features observed is the diversity in orbital shapes. While our Earth follows a nearly circular orbit, many exoplanets have highly elliptical trajectories, which can lead them to swing dramatically closer to their stars at certain points in their orbits. This suggests that exoplanets often experience gravitational interactions with other planets, causing their paths to shift over time. Another fascinating aspect of these orbits is their alignment relative to their host stars. In some systems, exoplanets orbit in a plane that is closely aligned with the star's own equatorial plane. This could indicate a relatively peaceful formation history, where the protoplanetary disk around the star was stable and uniform. However, astronomers have discovered systems where planets have orbits that are tilted at significant angles to this stellar plane, pointing to more tumultuous past interactions, possibly involving close encounters with other bodies or more complex migration patterns. What do these alignments and orbital shapes imply about the origins of these planetary systems? They suggest that the processes of planet formation are far more chaotic than once believed. Depending on factors such as the mass of the star, the presence of other planets, and even the gravitational influence of nearby stars, each system develops its unique configuration. For instance, a crowded environment with many large planets can lead to more eccentric orbits, potentially revealing vital clues about the influences at play during the early stages of the system's development. The observed variety of orbits and alignments in exoplanetary systems is a window into understanding not just the nature of those individual planets, but also the broader mechanics of astrophysics. By studying these characteristics, scientists can uncover hints about planet formation, the evolutionary pathways of planetary systems, and even the potential for habitability within these diverse worlds. The journey of planetary science has undergone remarkable transformations since the groundbreaking discovery of the first exoplanet in the early 1990s. Back then, astronomers identified a planet orbiting a distant star, marking a pivotal moment in our understanding of the cosmos. This historic observation opened the floodgates to a new realm of exploration, igniting our curiosity about planets beyond our own solar system. As technology advanced, so did our methods of detection. Initially reliant on techniques like the radial velocity method, which measured the gravitational influence of a planet on its star, scientists soon embraced a variety of innovative approaches. The transit method, which detects the dimming of a star's light as a planet passes in front of it, has become particularly fruitful. Telescopes like Kepler and more recently TESS have expanded our catalogue of known exoplanets dramatically, leading to the discovery of thousands of these distant worlds. Our understanding has also evolved in terms of the types of planets we find. We started with a focus on large gas giants mirroring our own Jupiter and Saturn, but we now recognize an incredible diversity of planetary types. From hot Jupiters, which orbit very close to their stars, to Earth-sized rocky planets in habitable zones, the variations are staggering. This diversity invites deeper questions about how planets form and evolve, and whether conditions might exist elsewhere that could support life. Moreover, the study of planetary atmospheres has taken center stage as we learn more about the chemical compositions of these distant worlds. By examining the light that filters through a planet's atmosphere during transits, scientists can identify which gases are present. This not only tells us about the planet's climate and potential habitability, but also provides insights into the processes shaping planetary systems. As we continue to explore and learn, our understanding of planetary science is transforming, revealing a richer and more complex universe than we ever imagined. The quest to understand worlds beyond our own has deep roots in the history of astronomy. Among the key figures who laid the groundwork for exoplanet research is the renowned Italian scientist Galileo Galilei. His pioneering observations in the early 17th century, made with one of the first telescopes, fundamentally changed how we perceive the universe. Galileo's studies of celestial bodies in our solar system prompted future generations to wonder about planets orbiting other stars. Fast forward to the late 20th century, and we find the astrophysicist Frank Drake at the forefront of exoplanet discussions. In 1960, Drake established the Drake equation, a formula intended to estimate the number of communicating civilizations in our galaxy. While primarily focused on extraterrestrial life, this framework highlighted the importance of knowing about other planetary systems, triggering an uptick in interest and research into planets beyond our solar system. Another pivotal figure is Michel Mayor, a Swiss astronomer who, along with his colleague Didier Queloz, made history in 1995. They became the first to confirm the existence of an exoplanet orbiting a Sun-like star, a giant planet named 51 Pegasi b. Their discovery not only revolutionized our understanding of planetary systems, but opened the floodgates for thousands of exoplanet discoveries that followed, dramatically shifting the field of astronomy. Lastly, we must mention the role of space telescopes, particularly the Hubble Space Telescope and the Kepler Space Telescope, which launched in 2009. Kepler's mission was specifically designed to find new exoplanets, transforming our ability to discover and study them. The insights gained from these astronomical endeavors have significantly enriched our understanding of the universe and our place within it, inspiring an ongoing exploration of the stars and the potential for life beyond Earth. Past scientific misconceptions about planets have considerably shaped the ways contemporary researchers approach their studies. These misunderstandings often stem from early observations made with limited technology, leading scientists of the past to draw conclusions that we now recognize as flawed. For instance, many believed that the planets moved in perfect circles and that the Earth was at the center of the universe, a view that was dominant until the observations of Copernicus and Galileo began to shift our perspective. These historical errors remind today's scientists of the importance of questioning established beliefs and remaining open to new evidence. The journey from a geocentric to a heliocentric model marks a pivotal turn in our understanding of the solar system. This evolution encourages a cautious optimism in modern research, pushing scientists to design experiments and observations that rigorously test hypotheses to avoid repeating the mistakes of the past. The recognition of past errors reinforces the practice of skepticism, leading today's planetary researchers to validate their findings through repeatable experiments and peer-reviewed work. Moreover, these misconceptions influence technological advancements and research methodologies. For example, once we understood that planets do not follow perfect circular orbits, it prompted the development of more sophisticated models and simulation software. Researchers now use complex algorithms and powerful telescopes, such as the James Webb Space Telescope, to explore the cosmos with precision unrivaled in earlier times. Each correction of past misunderstandings has allowed researchers to fine-tune their approaches, factoring in variables like atmospheric conditions and gravitational influences that were previously overlooked. Finally, education plays a significant role. The narrative of how our understanding has evolved is essential in teaching future generations of scientists. Incorporating the history of misconceptions into curricula not only provides context, but also instills an appreciation for the scientific method. We learn that science is a journey of revisions and adaptations, encouraging an ongoing quest for knowledge and ensuring that modern research methodologies remain ever more resilient against the allure of oversimplified conclusions. Through understanding our past, we empower our future explorations of the planets and beyond. The discovery of advanced civilizations on exoplanets carries profound implications for our own future. One significant aspect is the possibility of collaboration and knowledge exchange. If we find civilizations that have mastered technologies far beyond our current capabilities, we might have the opportunity to learn from their advancements. This knowledge could help us solve pressing issues like climate change, resource scarcity, and health crises, enabling humanity to evolve more rapidly in areas we currently struggle with. Moreover, the existence of intelligent life elsewhere prompts us to reflect on our own trajectory as a civilization. We could begin to understand the lifespan and sustainability of civilizations by studying their development. If advanced civilizations have thrived for thousands or even millions of years, this might inspire us to consider how we can extend our own existence without collapsing under the weight of our technological advancements and societal challenges. The study of their histories could offer us vital lessons on resilience, cooperation, and ethical governance. Conversely, the scenario of advanced civilizations introduces a note of caution. The potential for conflict or misunderstanding remains high, especially if such civilizations view us as a lesser species or if we misinterpret their intentions. It may also remind us that technological advancement does not always equate to moral progress. Understanding this dynamic could reshape international conversations about technology, surveillance, and our own responsibilities as stewards of Earth. Ultimately, contemplating the implications of advanced civilizations compels us to look inward. We are challenged to examine our own values and behaviors. This exploration could reinforce the necessity for global cooperation and unity as we face the vastness of the cosmos. Knowing we are not isolated can inspire a greater sense of purpose, urging us to become better custodians of our own planet and potentially a more enlightened part of a broader cosmic community. Transhumanism is a philosophical movement that advocates for the enhancement of the human condition through advanced technologies. At its core, Transhumanism explores the potential for humans to evolve beyond their current physical and mental limitations. This concept becomes particularly relevant when we consider the exploration of exoplanets and the quest for humanity's long-term survival beyond Earth. As Earth faces numerous challenges, including climate change, resource depletion, and potential existential threats like asteroid impacts, the idea of colonizing exoplanets emerges as a viable solution. In this pursuit, transhumanists envision a future where human beings are equipped with enhanced capabilities, such as advanced physical traits, improved cognitive functions, or even biotechnological adaptations that make it possible to thrive in alien environments. This futurist perspective encourages the development of technologies that could allow humans to withstand harsher conditions on distant worlds, such as reduced gravity or extreme temperatures. Furthermore, exploring exoplanets offers a unique opportunity for transhumanism to intersect with space exploration. As we search for habitable worlds, humans may need to rethink what it means to be human. If colonization becomes essential, our understanding of human biology might need to evolve. Transhumanists advocate for creating hybrid beings, combining human biology with artificial intelligence or enhancing our natural abilities through genetic engineering. This could enable us to adapt to various environments that current humans cannot survive in. The pursuit of exoplanets for humanity's survival is inherently linked to transhumanist